All right, so welcome to Chapter 19. This is going to be free energy and thermodynamics. And there's a little bit of crossover between this and elements of physics, but you'll quickly see that once we get away from some of the early definitions of thermodynamics, we're going to be applying these towards chemical systems fairly rapidly. And there's a little bit of math in this, but this is actually going to be a nice bit of a reprieve from our discussion of equilibrium right until the end. Because then at the very end of the chapter, which won't be this lecture, it'll be the subsequent lecture, we'll be relating concept of thermodynamics that we're introducing in this chapter back towards equilibrium constant. Okay, so with that introduction said, let's see what we can get started with. First law of thermodynamics. So first this really is kind of intended to be funny. I don't know how funny it'll be, but the idea being, like so many things in life and in chemistry, winning is hard. And so first law of thermodynamics is that energy cannot be created nor destroyed. And that's just a fundamental truth of the universe. You cannot come out on top on transitions in reactions in terms of energy. You cannot end up with more energy net in the universe than when you began any particular chemical transformation or any other process for that matter, because energy will inherently be dissipated and transformed and distributed in non-efficient fashions, which lead to increased entropy, which we'll discuss in a little bit. But this is why there's always losses in any kind of reaction, in any kind of physical interaction, and why the notion of perpetual motion is impossible. So, interesting. Here we go. Can I switch between? Interesting. I'm going to have to do this manually. Okay. Well, you can't see, but I'm having a technical flaw here, but I'll work through it. So, what I was just discussing, you can consider an energy tax. Not only can you not not gain energy, you can't even really break even in terms of efficiency because of the second law of thermodynamics. The tendency for energy to spread out or dissipate we're not being prevented to do so. So this means that we can't necessarily contain energy to do what we want, because in the action of doing what we want with energy, there will be numerous opportunities for that energy to be used in inefficient fashions. It will be lost to surroundings via heat or sound, or molecular motion inefficiencies, and friction, and so many other things. So in terms of chemistry, it's predominantly heat, but there's other mechanisms of energy loss, which we'll discuss. So let's talk about spontaneity in terms of chemical reactions and how it relates to thermodynamics, because we've been using the discussions reactions proceeding, not proceeding, reacting, not reacting, and we're going to start really moving forward with the notion of spontaneity of reaction. So thermodynamics is just a tool which helps us predict whether a process occurs under a given condition. And by that, it means will it proceed or not? And any chemical process that occurs without an outside intervention, meaning energy being put into that system, is called a spontaneous reaction. So another way to think of this is that a non-spontaneous reaction requires energy to be put into the system for that reaction to occur. It will not go off without a little extra boost. Now we can determine spontaneity by comparing the chemical potential energy of the system before a reaction with the free energy of the system after the reaction. And if the system after the reaction has less potential energy than before the reaction, this is considered thermodynamically favorable. And we've seen elements of this before, where we look at, oh no, let me see here. Need to select the draw function, apparently. Hold with me. So why? Uh-oh. Let me pause. Well, excuse the glitch. Apparently, it does not let you mark up PowerPoint slides if you have multiple PowerPoint presentations open simultaneously on your computer. So now that this has been fixed, let's get back to this discussion of before and after and energy levels. So I think a lot of you have seen this x-axis being the progress of a reaction, with your y-axis being your energy levels, and then you get this kind of graph where we have the reaction start point at 0, and then as the reaction progresses, we go through a transition state where we're at our highest energy, and for favorable reactions, as the reaction proceeds, we settle into where our products, some of our products have a lower energy than our reactants. And this difference is very important for determining the equilibrium and how far a reaction will proceed towards products. So what's really important to remember here is this particular example is a spontaneous example where the products, I'm going to go with a P, are lower in energy on the y-axis than the reactant. And you can use this synonymously with lower energy means more stable. Higher energy means less stable, or slash more reactive. Everything is trying to run downhill in nature. Whether it's a ball on a hill, it wants to run downhill. If you want to push the ball uphill, it requires energy. Chemistry is the same way, and molecules are the same way. In terms of potential energy, or chemical potential energy, everything wants to run downhill. So once we've invested enough energy for something to reach the transition state, here it has the opportunity to run either back downhill towards the reactant side or downhill towards the product side. And this will happen reversibly, except once it becomes a product, notice it has a much further lift to go back up that hill than it does to go from the reactant side up the hill. So in the end of a reversible process, it's going to favor the product side because of that larger difference, that larger lift to get back uphill to the transition state. And in this particular case, the product would be favored. Now, if we were to look at an example where, when we'll see this in a second, where we have something like this, where the reactant is actually lower in energy than the product, in this particular case, this would not be favorable inherently, because the product will be in higher energy than the reactant system. So one last caveat to this discussion, which is really important, this last bullet point. Just because something's spontaneous does not indicate the rate of reaction. Thermodynamics does not mean something is fast or slow. Spontaneity does not mean something's fast or slow. It means the reaction proceeds favorably. This can happen very quickly or it can happen very slowly. A really good example of this is rust. Rust occurs as iron oxide when iron, which is bare, is exposed to moist conditions in the presence of oxygen. And you get this oxidation effect where the iron becomes oxidized and becomes rust. Now, this happens spontaneously without the input of significant amounts of energy. However, it's a relatively slow process. And of course, conditionally, you can change the conditions so that it happens faster or slower or whatnot. But in the end, oxidation of iron to rust is a spontaneous process, but it's a fairly slow process. So spontaneity, remember, does not mean fast or slow. It just means the reaction proceeds favorably. So this is another way to look at potential energy, a couple different ways. And I just want you guys to try to get comfortable with the notion in terms of the universal concepts of physics that whether it's a physical potential energy or a chemical potential energy, a lot of the same concepts carry forward. So with mechanical potential energy, if you lift something up high, the higher it is, the more potential energy it has. until it hits its maximum velocity because wind force decelerates it. But that's a caveat. The same is true for chemicals. Now, the example here that we're looking at on the right side, on top we have solid sodium chloride in its crystalline form, and then we put it into water and it dissolves, where the crystalline form separates, and each of those cations and anions, instead of interacting with each other in ionic bonding fashion, now are interacting with the partial positive and partial negative charges of the water. And now what we'll see with the reason a salt like sodium chloride dissolves is because the system of dissolved ions in solution is lower in total energy, total chemical energy, than it was as a solid. That's why that spontaneously will separate those ionic bonds, forming new interactions between the ions and the water. But everything in chemistry can fundamentally be described in terms of this process, in terms of tracking chemical reaction, other than raw kinetics. Is it favorable? Is the product lower in energy, or is it unfavorable? Is the product higher in energy? This is another example which is worth looking at because it's an interesting one. We think of diamonds as spectacularly stable because they come deep from the earth, are forged under high temperatures and pressures and whatnot, and it's one of our pure sources of carbon. But if you look at carbon on a basic level, it turns out that graphite form of carbon is actually more stable / lower in energy than diamond. So given enough time, it would be considered spontaneous for diamond to reconfigure itself once removed from that high pressure situation to revert to graphite. Now, of course, this is going to happen astonishingly slowly. So another example of something being thermodynamically favorable not equating to something happening quickly. This is a really nice way to separate those things because this is, of course, a energy / reaction diagram that I'm not going to doodle, but it helps separate the kinetics versus thermodynamic components of chemical reactions. What we're talking about today is thermodynamics. We've already talked about kinetics. Thermodynamics is all about where you are in terms of energy of your reactants and where you are in terms of energy of your products. That difference here between products and reactants, whether it's positive or negative, is going to determine your thermodynamics of your reaction. What happens between reactants and your transition state is going to determine the kinetics of your reaction. So rate is going to be determined by your kinetics, and the favorability will be determined by your thermodynamics. So let's talk about spontaneity of processes in a little bit more detail and start giving some specific terms which are really important for describing these processes in terms of chemistry conversation. So spontaneous processes occur because they release energy from the system. And that's one way to view it. Coming back here, this would be a non-spontaneous process because the product is higher than the reactant, and because the products are higher in energy than the reactants, you have to put energy into that to make that proceed. Now, if, let's say, we were down here with our product, the delta would indicate that we have dropped in energy going from reactant to product. Well, what happened to that energy? That is that release of energy which this definition is describing. So most spontaneous processes are going to proceed from higher potential energy to lower potential energy. And these, because they release energy, are called exothermic. Exo being like exoskeleton, exterior, outside, releasing. But you can also have some spontaneous processes that proceed from systems of lower potential energy to higher potential energy, but these are endothermic. But that's conditionally, that's an odd definition because they're only spontaneous under appropriate conditions where you are putting energy into the system. So whether something's spontaneous or not, on some level, depends on the amount of energy that you are have available to you. So let's look at how something can absorb potential energy yet have a net release of energy. Well, this is a good one. So ice melting, right? Because we're all comfortable with that one. We're in Alaska. If you're watching this video from outside of Alaska, I'm in Alaska, and most of the students watching the video are in Alaska. But ice melting is something we all can relate to. So melting is inherently an endothermic process. It's taking energy from its surroundings to warm up. Yet ice spontaneously melts above 0 degrees Celsius. And this is that condition to which I was referring. If there isn't enough energy around, it's not going to drive the process because it's inherently endothermic. But it will spontaneously melt above 0. So when a solid melts, the particles are going to have more freedom of motion. We're going from this nice, orderly, crystalline, solid structure to a liquid where, on top of just vibrational motions, you also get the physical ability of them to rotate in 3 dimensions, to move back and forth and up and down in all 3 dimensions and whatnot. So substantially more freedom of motion in the liquid form. And the more freedom of motion increases the randomness of the system, and the system becomes more random, energy is released. And this type of specific energy, this random energy, is called entropy. And entropy, for those of you who continue on in your chemical education, is going to become incredibly important in a number of our courses, but in particularly in Biochemistry 1, when we discuss how entropy of the system actually drives spontaneous formation of lipid structures and 3-dimensional protein collapse, and why entropy is so spectacularly important for the biological events, chemical biological events, which allow life to be possible. So even though we're going to be talking about ice in this example, as you get comfortable with the concepts of entropy and you proceed through your science education, this is going to be astonishingly important in some of our later courses. So another example of increasing entropy is the evaporation of water, where we go from liquid form to gaseous form, where you have this 3-dimensional ability to translocate and rotate and move in liquid form, but then in gaseous form, you have a lot more space between the actual molecules, and you also typically have a faster degree of motion and rotation in those molecules. And this is an example of an increased entropy as well. A third example would be sublimation, where you go just straight from solid to gaseous form, and we see that up here all the time as well. Third example, dissolving of water. And we talked about this just very quickly, but what's leading to this is not just the energy level of the ions, orderly bonds between the sodium and the chlorine in this crystalline salt form that we start with, but it's also for the entropy in the reactant side and the product side. Because in the product side, we have substantially higher entropy, because instead of this nice orderly structure of a crystal, we have these ions moving all about the place. And so this is going to have a significant increase in entropy, which is thermodynamically favorable because the universe tends towards chaos. And that's, physicists are going to cringe when I say that. But energy tends to dissipate. Things like to be distributed as evenly and as far apart as possible. And so when we're looking in terms of how things want to behave in terms of energy, increased entropy is favorable. So because one of the reasons that this reaction of dissolving water, a salt into water, is favorable is because of that increase in entropy. So let's zoom in even more. Second law of thermodynamics. Entropy is a thermodynamic function that increases with a number of energetically equivalent ways to arrange the components of a system to achieve a particular state. Well, that's a nice way to say that the more ways you can organize a particle, either in its macrostate or its microstate, the higher the entropy is going to be. So that's why a liquid will have higher entropy than its solid, because there's more way you can arrange the atoms three-dimensionally and vibrationally. And why a gas is higher entropy than a liquid, for the same rationale. And we'll go into that in a little bit more detail, but that's fundamentally why. The second law of thermodynamics states that for any spontaneous process, the entropy of the universe increases. So energy tends towards entropy, increasing, always, for spontaneous processes. That's one of the things that makes them favorable. Now, it's also important to recognize that entropy is a state function. It's all about its final state minus initial state. The path it takes between the final state and the initial state have absolutely zero impact on the delta. What matters is where you started and where you ended. And that's what a state function is. So generally, we look at entropy in terms of joules per mole Kelvin. And we can look at entropy and thermodynamic factors in a variety of different ways. One way we can consider entropy is through Boltzmann's constant. And Boltzmann's constant is just a proportionality factor that relates the average relative kinetic energy of any particle in a gas, specifically a gas, with the thermodynamic temperature of that gas. So what we're looking at with this definition of entropy is that it relates Boltzmann's constant, which is just a term of joules per unit Kelvin temperature of a particle in a gaseous phase, to W, which is the number of energetically equivalent ways a system can exist, which is a unitless. And that W is talking about the combination of macrostates and microstates, which we'll elaborate on in a few slides. Here we go, macrostates, microstates. So macrostate is a state defined by a given set of conditions, pressure, volume, and temperature. And a microstate is the exact way the internal energy is distributed among the particles at any one instant. Zoomed way in, what are the particles doing and how are they differing from moment to moment to moment? And W, apparently, for this definition, is not a macrostate definition, it's a microstate definition. So let's look at microstates. In this particular system, we have energy on the y-axis, and notice we have an energy of 2 joules, where both particles, the red particle and the blue particle, are on the same energy level, but we can have a microstate between these two particles where blue is at 1 joule and red is at 3 joules, or we can have blue be higher at 3 joules and red be lower at 1 joule. Now, what's important is that the sum of all of these are 4 joules between the two particles. So the net energy of A and B in both microstates is identical. Now, as you add more particles to this, the more numbers of ways that they can, or the number of levels that they can exist at. Maybe there's 4 levels instead of 2 levels, or 10 levels instead of 2 levels. It becomes astonishingly complex very quickly, the number of microstates. What's important is, are the microstates increasing for a system or decreasing with a system? Because that's what's going to determine the ability to distribute your energy over as many microstates as possible, which will increase your entropy. I think this has been adequately covered. Let's just move on to the next slide regarding macrostates and probability. So what we just looked at was microstates. For macrostates has to do with physical distributions of particles. So this is a really nice, simple way to just look at it. If you have 4 gas particles in a system between 2 sides that are connected by a tube, you can have state A, where all 4 particles are on the left. You can have state B, where all 4 particles are on the right. Or you can have state C, where particles are evenly distributed with 2 particles per side. And this is just based on motion between the particles. Now, what turns out is that state C is substantially more probable than states A or B. And notice that's because they're evenly distributed. Getting everything onto one side or the other probabilistically is like flipping the coin and coming up heads every single time. And this is only with 4 particles. Imagine how improbable it would be to have everything with billions of particles on one side and not on the other, versus having them evenly distributed. And this is why we see diffusion. We see energy diffuse from regions of high energy to low energy. We see salt diffuse from a point of high concentration. So you pour salt water on one side of a beaker, it's going to generally distribute itself evenly across the entire beaker over time. If you put gas into a evacuated space, it will evenly fill that space. And this is because of trying to balance the probability of the most likely distribution of macrostates. And apparently I talked through the entire second slide without intending to, but state C is 6 times more probable than A and B, but this is only with 4 particles. Once again, we're talking about trillions and trillions and trillions of particles in so many systems. And what's really important to look at here is this particular diagram, is that all of these microstates, all the possible microstates that we're showing on the right side, have the same fundamental macrostate. We have 2 particles per side, and they'll have an average of the same energy level if particle height is related to energy level. So in this particular case, we have 6 different particle arrangements that result in the same macrostate, which means we can have, and this is only with 4 particles in the system. So I know this is a little bit simple in its delivery, but if you think about the effects of these trends applying towards much larger chemical systems, you can get a sense, I think, relatively quickly of what we're working with. Now let's take a look quickly at entropy and state change. We've talked about solids and liquids and gases a little bit, but it's worth revisiting and zooming in a little bit more. So when materials change state, the number of those macrostates change. And the more energetically equivalent configurations the molecules have, the more macrostates are possible. So gases have the highest number of macrostates available, higher than liquids, which are also have more macrostates than solids, just because of the ability to put the molecules into more diverse positions through vibration, rotation, and translation. And this is what it looks like if we're looking at entropy on the y-axis versus temperature on the x-axis. As you increase temperature, moving from left to right, we see a increase in entropy, which is the solid phase. So as we start at 0 entropy, which is incredibly cold, 0 Kelvin, which is incredibly cold, to minus 273 degrees Celsius, and we start heating a solid slowly, we see that the entropy does increase slowly. And then, because we're increasing that vibrational motion in the molecules, but then we run into this transition state, which is the freezing point, which is defined between the solid and the liquid. And this is where melting of the solid occurs. Notice how much the entropy increases instantly between the transition between the solid phase and the liquid phase. Also note, the same thing happens as we continue to heat the liquid. It's slowly increasing the amount of entropy of the liquid because of that vibrational and translational character of the molecules being excited by all this new thermal energy. But then we run into the evaporation of that liquid, and when it goes from liquid to gas, it instantly has substantially higher entropy because of it. Now, this large jump in entropy doesn't come for free. It takes a lot of energy, if you guys remember from last semester, to go from a solid to a liquid or liquid to a gas. And this is why if you're measuring the temperature of a liquid as it's approaching boiling, you'll see it moving relatively quickly because the liquid's being heated fairly linearly, and then as it approaches that transition, it just hangs out for a minute. It stalls and the temperature stays put, but you're still pouring energy into it. And what that energy is doing is, instead of increasing this thermal excitation, that thermal energy, instead of making the temperature of the liquid go up, is being consumed to overcome this large jump in entropy. So a really cool effect that we see here in Alaska, and you guys have all probably been appreciating it for the last month and a half, is in fall, temperatures start to fall fairly quickly. And then everyone notices they kind of level out right above freezing. That temperature comes crashing down. It was nice, and now it's 50, 40, mid-30s. And it's just hanging out oddly right in that mid to low 30s, and it just stalls out. And the reason it's stalling out is because even though the system that we're in is getting colder, or is losing thermal energy because of our place in the universe and the rotation of our planet relative to the sun, we have a lot of water in our air, and we have a lot of water in our environment from all this rainy fall weather. And all that water to freeze has to go from a liquid to a solid, and we have to pull all of that thermal energy out of it. So that actually changes the environment, the atmosphere's temperature. It makes it resistant to temperature change as we're making that transition, which is why we get this odd stall where fall kind of lingers before everything freezes up. And then once it's frozen up, it's like, all right, cool, we're solid and we can go and get colder again. But we're in the middle of experiencing a thermodynamic stall between phase changes right now as we speak. So, back to the universe, I suppose, and entropy. To summarize, the second law of thermodynamics demands that entropy of the universe increases for spontaneous processes, but processes like water vapor condensing are spontaneous, even though water vapor is more random than liquid water. Caveat being under specific temperatures. If a process is spontaneous, but the entropy change of that process is unfavorable, there must have been a large increase in the entropy of the surroundings. And finally, the entropy increase must come from heat released by the system for the process to be exothermic. Okay, so we're going to look at two different examples really fast of talking about the system and the surroundings and the universe. So in this particular slide, when the entropy change in a system is unfavorable, which is negative, which we're seeing here for the system, the entropy change of the surroundings has to be favorable, positive, so that the entropy of the universe increases. So every time we're talking about thermodynamics, you have to be very, very clear about what your system is. What's your system? What's your surroundings? And of course, we have a sense of what the universe is. So in this particular case, we're seeing an increase in entropy of the universe due to the large increase of entropy for the surroundings, despite the negative increase of entropy for the system. Conversely, we can look at this with water freezing, because this is that system surroundings, how much energy is available at high temperatures and low temperatures. At low temperatures, where freezing of water is spontaneous, the entropy is going to be positive, because despite the change in entropy being negative for the system, we have this increase in entropy for the surroundings. However, at high temperatures, it's not spontaneous, because the sum of delta entropy for the universe, which is your system plus your surroundings, is going to be net negative. This is why some reactions are spontaneous at certain temperatures and not spontaneous at other temperatures. Specific to entropy, we'll also see once we get into enthalpy and delta G that there's other thermodynamic effects that weigh in on that as well. So let's talk about heat exchange and the change in entropy of surroundings specifically for a second. When a system process is exothermic, it adds heat to the surroundings. And this increases the entropy of the surroundings, because heating something up is going to increase the excitation. So when a system process is endothermic, it's going to be taking heat from the surroundings, decreasing the entropy of the surroundings. Because just when we were looking at that phase change chart, if you're pulling heat from the surroundings, it's going to have less thermal energy exciting those molecules and atoms and particles, and it's going to subsequently drop. The amount the entropy of the surroundings changes is going to depend on its original temperature. So the higher the original temperature, the less the effect of the removal of the heat is going to have. It's just like taxing, people who are billionaires. If you tax billionaires, it's going to be relatively trivial to them, because in terms of net effect on their change. But if you don't have much to begin with, it's a lot harder. So, clearly I'm not an economist, I'm a chemist, so that's just an analogy. So what about the temperature dependence of the change in surroundings? There's a greater impact on entropy when heat's added to the surroundings that are at lower temperature than at higher temperatures, which is what we were just getting at. So water freezes spontaneously below 0 degrees Celsius because the heat released on freezing increases the entropy of the surroundings enough to make the delta S positive. But above 0 degrees Celsius, the increase in entropy of the surroundings is insufficient to make that delta S of the universe positive. So, quantifying entropy changes in surroundings. The Q, remember Q is heat of a system, which under constant pressure and temperature, Q is going to be used interchangeably with H, enthalpy, for the context of this course in particular. So heat of the surroundings is going to be equal to the negative heat of the system. because the entropy change in the surroundings is proportional to the amount of heat gained or lost. So entropy change of the surroundings is also inversely proportional to temperature. Which we see here, where the change in entropy for surroundings is going to be equal to the negative change in enthalpy of the system divided by temperature, in absolute temperature. This, of course, only holding for systems where we have constant pressure and temperature. So let's do a couple quick solutions. Let's get back up off of conceptual land, where we've been for a while, and start applying these concepts towards problem solving, because in the end, we're not going to just be talking about enthalpy, entropy, and thermodynamics. We're going to be asked to solve problems specific to this system. So let's look at this first one. It's fairly straightforward. Calculate the change in entropy that occurs in a system when 25.0 grams of water condenses from a gas to a liquid at the normal boiling point of water, 100 degrees Celsius. And to work through this, because condensation is occurring at boiling point of water where the temperature is constant, you can use this equation 19.1 from the text to calculate your level of entropy. Delta S is going to equal Q divided by T. So in this particular case, we need to look at all the necessary quantities, and of course you're not going to have to memorize these. They're either going to be given, or you can look them up on the tables that are included in the book. But look up the value of the enthalpy of vaporization for water. Enthalpy of vaporization is 40.7 kilojoules per mole. And the enthalpy of condensation is the same value, but it's opposite in sign. Vaporization, condensation, opposite processes, opposite sign. How much is consumed? Remember, delta is always final minus initial. So keep that in mind when you're looking at your positive and negative signs for these processes. And so calculate the temperature in K. Well, all we have to do for this is look at temperature in Kelvin equals temperature in Celsius plus, oh, wow, this is really all we're doing, 273.15, and that's going to be 373.15 Kelvin equals 100 C. Because whenever we're doing thermodynamics, we have to have things in Kelvin. We can't do it in Celsius. And then we can plug these values into our simple equation to determine the change in entropy, where Q is going to be 25 grams, where Q equals mc delta T, 25 grams times, and we want to get rid of grams, so we're going to divide by 18.02 grams per mole, multiply by our negative 40 times 10 to the third joules per mole, which is our thermodynamic term, and then divide that by the temperature, and we're going to get negative 151 joules per Kelvin. Let's look at another example here that is slightly more complicated. And this has three parts. So let's look at the combustion of propane. Propane is our C3H8 gas, and it's going to react stoichiometrically with 5 equivalents of oxygen gas, forming 3 equivalents of carbon dioxide and 4 equivalents of water vapor. And the delta H for this reaction is negative 2,044 kilojoules of energy. So first part, calculate the entropy change in the surroundings when this reaction occurs at 25 degrees Celsius. Second part, determine the sign of the entropy change for the system. Third part, determine the sign of the entropy change for the universe. Is this reaction spontaneous? And you guys have a little intuition for combustion of propane, so I suspect you'll be able to use a common sense double check on that third one. But jumping into A. So A, remember, calculate the entropy change in the surroundings when the reaction occurs at 25 degrees Celsius. So if we're given Celsius, we have to find Kelvin. We'll just add 273. So at 25 Celsius, that's 298 Kelvin. So that's going to be our temperature term. And so our delta S of the surroundings is going to equal the minus delta H for the reaction over T. So for the reaction, in terms of kilojoules, it's negative 2044 kilojoules divided by 298 Kelvin. And this is going to give us a positive 6.86 kilojoules per Kelvin, which you could report in joules if you were inclined to do so. Now, the second part of this is determine the sign of the entropy change for the system. So, in this particular case, we have an increase in the total number of moles of gas. We're going from 1 mole of propane plus 5 moles of oxygen is 6 moles of gas to a total of 7 moles of gas as product. So right away, we're ending up with more moles of gas than we did before. We know this is going to be a positive change in entropy for the system. And finally, what's the change of energy for the universe? Is it positive or negative? Well, in this particular case, the change of entropy for the system is positive because it was very positive. We know the change of entropy for the surroundings is positive. Therefore, the change for the universe is going to be positive. It's solved. So in this particular case, change of energy for the universe is positive, and therefore the reaction will be spontaneous. This would be a really good time. We have this other practice problem that's very analogous, and I recommend working through these A, B, and C steps and just getting comfortable with applying the same logic that we just flowed through to another problem to really ingrain the process a little bit. Then once you're done with that, jump into the next slide. We're going to work through a few more slides, and that'll be the end of this particular lecture. Having worked through that problem, hypothetically, we'll jump into Gibbs free energy here. So Gibbs free energy, we've been looking at entropy exclusively, but entropy isn't the only thing that matters in terms of thermodynamics. We have a term, let's see here, Gibbs free energy, G. And what it is the maximum amount of work energy can be released to the surroundings by a system under constant temperature and pressure. And we often refer to it as chemical potential because it's really similar to the storage of energy in mechanical systems. So the relationship that's really important for everyone to remember here is this third bullet. Delta G equals delta H minus T delta S. So change in Gibbs free energy is going to equal the change in enthalpy of a system minus the product of the temperature in Kelvin times the change in entropy of the system. And because we've already noticed that change of entropy of the universe determines spontaneity, we routinely and more frequently use delta G to determine reaction spontaneity. I'm going to lean on that pretty much for the entire second lecture, because if delta G is negative, it's spontaneous. If delta G is positive, it is non-spontaneous. And because of this relationship that we've already seen, if delta S for the universe is positive, then delta G is negative when spontaneous. But remember, delta G equals delta H minus T delta S. That has got to be burned in your brain. So, jumping more into Gibbs free energy, delta G. I know I just said it. I'm going to keep saying it because the more we say it, the more it might burn in there. A process is going to be spontaneous if delta G is negative. So there's a couple different ways we can reach a negative delta G, because delta G equals delta H minus T delta S. The interaction of the first term and the second term can lead to different system combinations of things happening, leading to something being spontaneous or non-spontaneous as a chemical reaction. So it can be negative if delta H is negative and delta S is positive. It's exothermic and it's more random. Excellent. It can be negative if delta H is negative, significantly negative, and delta S is negative, but not dramatically negative. So this would be a good example of a low temperature reaction. Delta G can be negative if delta H is positive, but only a little bit. Yet we have a very positive delta S and high temperature, which amplifies it. And delta G can be will be positive if delta H is positive and delta S is negative. So anytime you have a positive entropy and a negative, a positive enthalpy and a negative entropy, delta G will be positive, and it will always be spontaneous at any temperature. So what if delta G is equal to 0? Well, that's at equilibrium. So that's a very common multiple choice question regarding something being in equilibrium. When delta G is at 0 for a system, that reaction is at equilibrium. So if it's negative, spontaneously reacting, meaning moving towards products. If it's positive, it is non-spontaneous, favoring reactant. If it's 0, it's at equilibrium. And this is a really nice way to visualize that relationship. So in this particular reaction, we have nitrogen gas reacting with 3 equivalents of hydrogen gas reversibly forming 2 equivalents of ammonia gas. And notice that if we have pure ammonia, it's going to be out of equilibrium and head backwards towards our reactants, which we're going to see in an equilibrium mixture. And if we were to start with pure nitrogen and hydrogen, it's going to be heading favorably back towards ammonia. And our equilibrium of our mixture is going to occur when delta G is 0. So one thing that we have to include is standard conditions, because I keep saying at this temperature, at high temperature, at low temperature. It can happen spontaneously here, but not necessarily here. And that's because our universe is complex. But one of the things we can do to strip away some of that complexity when we discuss thermodynamic properties of a chemical reaction is to refer to chemical reactions in terms of standard states. And that takes some of the ambiguity about the conditions away. And we can see them for what they are under standard state. And then we can add complexity as we see fit. So the standard state of a material is just a defined set of conditions. And for gases, standard state is 1 atmosphere of pressure. For liquid or solid, which is in pure substance, at 1 atmosphere, the temperature, which usually defines standard state, is 25 degrees Celsius. Usually. And standard state for concentrations is classically 1 molar, or 1 mole per liter. So these are usuallys. For the context of this course, it will be almost exclusively. But when we get into biochemical systems, there's very rarely a biochemical system where a solute is at a concentration of 1 mole per liter. Usually it's much, much, much lower. We're talking millimolar or nanomolar concentrations of some things. And because of that, some biochemical systems have different standard states at which they use. So, or they're just modified strongly. But those are all things down the road. It's just references for where this might go. In the context of this course, standard state, 1 atmosphere, 25 degrees Celsius, or / 298 Kelvin, and 1 molar. So let's do one more problem, and then we're going to call it a day on this lecture, and we'll pick it up and wrap up the chapter with a subsequent lecture. So consider the reaction for the decomposition of carbon tetrachloride. So carbon tetrachloride is carbon with 4 chlorines attached to it, and it is going to react forming carbon and 2 equivalents of chlorine gas, and the carbon is going to be in the form of solid graphite. We have a delta H for this, which is positive 95.7 kilojoules, And we have a delta S for this, which is also positive, 142.2 joules per Kelvin. So A, calculate delta G at 25 degrees Celsius, standard state, and determine whether this reaction is spontaneous. So remember, delta G equals delta H minus T delta S, and we have all of the things we need for that. If the reaction is not spontaneous, for part B, at 25 degrees Celsius, determine at what temperature, if any, the reaction becomes spontaneous. So for part A, we're just going to plug in. Well, first we should probably convert our temperature to Kelvin. It's 25 degrees Celsius, so it's going to be 298 degrees Kelvin. And then we're going to substitute everything in. We don't have to rearrange because delta G equals delta H minus T delta S. And remember, because we're subtracting these, we have to have the kilojoules become joules, or the joules become kilojoules. It's just easy to make kilojoules joules. So in this case, we're going to have a plus 95.7 times 10 to the third joules minus the product of 298 Kelvin times 142.2 joules per Kelvin. Kelvin units cancel, everything becomes joules, and we end up with 53.3 times 10 to the third joules. This is a positive delta G, therefore at the temperature of 25 degrees Celsius, this is not spontaneous. That shouldn't surprise you, because it would be odd for a liquid carbon tetrachloride to spontaneously become graphite under what we consider normal temperatures of 25 degrees Celsius. So let's figure out what that is. We're probably going to have to solve for T. So to figure out at what temperature this would become spontaneous, what we're going to do is set delta G to 0, because that's equilibrium, and every degree above that fractionally will drive it into spontaneity. So delta G equals delta H minus T delta S. Let's solve this by rearranging for T. And actually, my favorite way to do this is not to substitute, but to rearrange first. So I like to take delta G equals delta H minus T delta S. And then what I would do, preferably, is I would take T delta S equals delta H minus delta G, and then T equals delta H minus delta G over delta S. Of course, delta G is going to be 0, so that's going to fall out. It's going to be delta H over delta S, and you're going to get the same answer regardless, 673 degrees Kelvin. So that's not too complicated. To leave you guys with a practice problem, go ahead and run through the same logical sequence that we just ran through, but do it with a different example. In this case, we've got a different reaction with C2H6 reacting with hydrogen gas to form C2H6. Did I say that twice? I may have said that twice. But they give you the enthalpy, they give you the entropy, they give you the temperature, and they're just asking for the exact same outcome. So run through this really fast, get comfortable with it, and we'll pick this up with the third property of thermodynamics, third law of thermodynamics, and start adding a little bit more complexity to the things that we've introduced in this lecture. So I'll be talking at you shortly.